Anyway, some people know me, some people don't know me. So my name is Stefan Schafföner. I'm from Bayreuth in nice Franconia in Germany. And so I also would like to appreciate my collaborators. And there we go with the laser. So we have Nico Langhoff and Günther Motz, who are the group leaders at the chair. The PhD students at our chair, and as well the colleagues from the chair of macromolecular chemistry too. So CMCs is a very interesting topic because you have to work together with a lot of different fields, and you have to not only understand ceramics, but you also have to understand polymers. And so that's why it's a very interesting field, but also, let's say, challenging. So I don't have to explain so much actually what are CMCs, but I also realized you have to explain ceramics a lot to people who are not familiar with ceramics, and most people are not familiar with ceramics, and even less people are familiar with ceramic matrix composites. So even in the field of ceramics, people don't know that this kind of material actually, or these kinds of materials very much. And I think one of the main advantages of ceramic matrix composites is, and that is not so much as I would say emphasized, is that you have the advantages of textile technologies. So that means actually you can use their developments actually to our benefit. And also when it comes to polymers, we can use their developments actually to develop new ceramic matrix composites. So that means a transfer of technologies to the field of ceramic matrix composites. And that's also something, let's say, what we do a lot in Bayreuth. So I don't have to explain that much to you, but yesterday actually I gave a talk in Darmstadt. I had to explain very much actually what are ceramic matrix composites and what is their advantage. Okay, and we have different applications, and in Bayreuth we work a lot for, I would say, at least 20 years on carbon fiber reinforced silicon carbide, which is processed by liquid silicon infiltration, and that is still one of the main fields in Bayreuth. And we have, let's say, different applications. We already have the brake disc, so we have people from the brake disc industry also here today. And especially in Italy, it's still the largest application at the moment, I guess, for CMCs, also processed by liquid silicon infiltration, but also which is picking up quite rapidly now is space applications, as well as, let's say, we also have space applications here, but let's say military applications in the end. So. As I was saying, the big advantage for processing CMCs is that you can use developments in the field of polymer matrix composites for the and then transfer these technologies to ceramic matrix composites. So that means actually here we have this liquid silicon infiltration process. So you start with the raw materials with carbon fibers as the reinforcement phase, and then also you have thermoplastic or thermoset matrix in terms when you process a CSIC. And here especially you have new developments in the field of polymers, so thermoplastic polymers, and also the shaping technologies of the CFRP. So additive manufacturing, even in the field of PMCs, is developing rapidly. And then you can use, and what we do right now is actually using different polymers as well as new shaping technologies for CFRPs to process actually the preforms. Then the pyrolysis takes place. If you change here the processing here, you also have to understand the pyrolysis, and then obviously also the siliconization. So, and one aspect which is always important is if you have different polymers, is that you have to ensure good infiltration of the carbon fiber bundles in order to protect the carbon fibers during siliconization, and also to have a good load transfer later on. And the polymers, they have to have a high char yield, which is also not so easy actually to realize. So actually this is often these polymers which have a high char yield, actually their viscosity is actually quite high, so that means actually the processing is quite complicated. So currently, as many people of you know, we use thermoset polymers, which have their advantages. I mean, first of all, they are available, we understand them, they have been tested for a long time. They also have the advantage that they are actually not remelting during pyrolysis, so they have a good stability. They also have a low viscosity, so that means we have a good fiber bundle infiltration. However, one big disadvantage is that they have a condensation reaction. So the condensation reaction induces porosity, for example, and porosity then is impairing your mechanical properties. You also have usually, let's say, long processing times. Well, I wouldn't say that's the main issue. I mean, but nevertheless, you, for example, don't have recyclability, and you also have the curing, which is necessary. You have health issues, so there are a lot of issues. And one big aspect is also that, let's say, a lot of new technologies in the field of PMCs, so in the field of polymer matrix composites, are not based actually on thermosets, but actually on thermoplastics. So that's why we in Bayreuth actually explore these, let's say, the processing of thermoplastics recently actually quite a lot for the processing of ceramic matrix composites. However, not all, actually only few thermoplastics, let's say, are suitable as a matrix material. First of all, most important is the char yield after pyrolysis. And also, disadvantage, as I was saying, is the high melt viscosity. And usually, if you think about thermoplastics for these kind of applications, you end up with so-called high-performance thermoplastics, which are usually, for example, here polyether ketone or polyether ketone. So that means actually these are like polymers that have like a ring as a backbone. And that's why also they have a high char yield after pyrolysis, which is the main reason actually. So what we did, for example, is first of all, and using these thermoplastics for additive manufacturing, and because they are remeltable, you can actually then also use them for additive manufacturing. I will show later on. And the second aim, which I was also talking about, is developing new fibers, because usually you have the problem that either you have carbon fibers or you have ceramic fibers. And the carbon fibers, they oxidize, let's say, at 450 degrees Celsius, and then you have ceramic fibers. But these ceramic fibers, they are quite expensive. And so, so you have, let's say, a price gap, and you also have an a temperature gap. And that's why the aim of another project was actually to develop our fibers from the point of properties, from the oxidation point of view, that are between carbon fibers and silicon carbide fibers. This is a development actually that started some years ago in the group of Günther Mutz. And here, for example, we process the fibers by electrospinning. So we also have people here who like electrospinning a lot. We have a polymer solution here. Then we have electric field. We also, the dissolvent here, for example, is evaporating, and then actually the ceramic fiber forms here. So actually it's not a ceramic fiber, actually it's a polymer fiber, because later on you have a pyrolysis step also for the ceramization. So in this case, we use polyacrylonitrile and organosiloxanes as the polymers, and they then form a copolymer, and then we have these kind of non-wovens later on. So we did this for non-wovens, but we also recently did this for long fibers, so for continuous fiber production actually, which was just published 2 days ago, the paper. So sorry that I did not include it yet. So first of all, additive manufacturing of CMCs. This is a project that is about to end. We are currently exploring new funding venues. And in this case, we use so-called fused filament fabrication. I will explain this here. So what you have here, you have a filament. That means you have a polymer filament, which is filled with carbon fibers. And in the project, we used commercially available filaments, which are actually optimized, let's say, for the processing of CFRP. So they're not optimized for the processing of ceramic matrix composites. So that means actually you have to work on the filaments a lot. So these are short carbon fiber reinforced filaments, but there are also tapes available with continuous fibers. And the big advantage is that it's a quite rapid technology. It's also an established technology in the last 15 years in the field of CFRP production. And how does it work? Actually, you have a thermoplastic that is melted up, it becomes viscous, you can lay it up, and then you can process actually quite complicated shapes. So you have one big advantage. First of all, you have a near net shape processing. That's one aspect, and because that's even more important for ceramics than for all other kind of materials, because ceramics are so hard, so they're difficult to machine. And people who work with ceramics know that actually a lot of costs, actually, and also processing time is associated with the hard machining of ceramics. So actually, you want to avoid hard machining as much as possible. And the other aspect is that you save fibers, because if you have near net shape processing, you save a lot of fibers, which is also cost reduction. And that is important for CMCs a lot because, as you know, ceramic matrix composites, they actually have the big disadvantage of a high price. Okay, so here we have this kind of, there we go. Okay, so one big aspect is if you use thermoplastics and if you would remelt them or let's say heat them up again for pyrolysis, what would happen, they would remelt and then you do not have a form stability. So that's why actually you have to introduce a cross-linking step. And PEEK, for example, has the interesting aspect that it reacts with oxygen below the melting temperature. So, which is a disadvantage actually for PEEK if you want to join PEEK samples, for example, but it becomes an advantage for us because it becomes a thermoset material at below the melting point if you introduce oxygen into the microstructure. And then you have this kind of cross-linking here, so it's a thermally oxidative induced cross-linking. And so this step is crucial in order to have the form stability during pyrolysis and then later during siliconization. And here, so it's actually, let's say it's a kinetic process, so that means temperature is very important and time also becomes important. Time becomes important, especially if you have larger shapes. For smaller shapes, it's relatively easy, let's say, but if you have larger shapes, you have to understand your cross-linking actually quite well. And so you have a processing window. We recently explored this processing window quite intensively. And so the temperature at the moment, so you see the current parameters, I think, were published recently. And so you see it's allowed 48 hours, so it's a quite long time. So let's say the disadvantage of long processing times is still present. There are other ways to for the cross-linking, but this is the easiest one. But if you use, for example, acids also, it also can be done. So cross-linking is essential, and still, let's say, to shorten the processing time is still has to be investigated. So the other aspect is later on, if you have during the pyrolysis, you induce also porosity. So this is a study from 2021, so some years back. So that means you have porosity. So the porosity is, you have to have porosity later on during siliconization, but of course you want to reduce the porosity as much as possible. So in this case, for example, you see here, for example, the porosity was quite large, and here you can see the, with the, let's say, white ones, the white lines, this is the residual silicon, but nevertheless, it was possible, and this was the first study in 21, that we can produce carbon fiber reinforced silicon carbide using this process. So that means we then went a step further to optimize this process, but if you come to fused filament fabrication and if you study the influencing factors closely, then you realize, okay, there are a lot of factors for additive manufacturing that you can change and that you can alter, and that also changes the processing and therefore the microstructure and the properties and so on. So that's why we had to make a selection. And in this case, the easiest one is first of all the printing direction. And so we have three different directions. So we have 0 degrees, we have 90 degrees, and we have plus minus 45 degrees. And then we have the so-called infill density. So that means if you have the plane, that means how much actually of the area is filled in with the filaments. So you have 100%, you have 90 and 80%, and then you have the layer height. So that means how thick is actually one layer. And this was investigated with a statistical design. So you see already the microstructure was quite different. And what is also very important for the cross-linking is the internal surface area, which was then also investigated. And because you have to have an internal surface area for the cross-linking so that the air actually is possible to interact with the polymer. And here you can see the after pyrolysis, so this is 90 degrees, 0 degrees, you see, for example, deformation or cracking. But if you do like a plus minus 45 degree printing, you realize actually that the shape is quite homogeneous, and also that you have a quite uniform shrinkage, which is also important because we have the carbon fibers which are impairing the shrinkage. So if you have perpendicular to the fibers, you have a quite large shrinkage, but in fiber direction, the shrinkage is actually negligible. So that means that's why the reason is plus minus 45 degrees Celsius, so that you have a uniform shrinkage in every direction, more or less. Here you can see the bulk density. So you have the as printed, and you see, for example, the layer height. So that it's important, but especially here, if we have the layer height for the mechanical properties, so that means the smaller height of the printing layers is improving the mechanical properties, and also, let's say, the strain. And at the moment, we have actually now the newest samples are actually not 0.5, but about 0.4 with a commercial filament. If you use better filaments, actually, you get also better elongation and strain at fracture, which we already investigated. So here you can see some samples that we have processed. I can also give you 2 samples that were recently processed at the chair. I also like, it's always interesting when the PhD students come up and they say, oh, we printed something new, and it works actually quite well. If you understand the printing quite well, actually it's possible to make even larger shapes and also complicated shapes. And you see, and siliconization has the big advantage. It's a surface, let's say, controlled process. So that means actually even complicated shapes can be siliconized if you use the right amount of silicon. And even so, these commercial fibers, they had a fiber length of about 500 microns. And even there, you already see some kind of small pull out, but nevertheless, 500 microns, as everyone knows in this field, is not sufficient as the fiber length. So, second aspect, I still have time. And because we started like a little bit later. So we have electrospinning of hybrid carbon ceramic nonwovens. These was a collaboration with the chair of macromolecular chemistry. And in this case, we used so-called copolymers of polyacrylonitrile and polysiloxanes, commercial polysiloxanes. We like to work with Durazane 1500 and Durazane 1800 a lot, and this was a collaboration some years back with a group from Brazil, and showing that the oxidation of this, it's a function of the amount of the polysiloxane addition. And there's actually a cross-linking reaction also with the silicon hydrogen bonds and the cyanide bonds leading to this silicon nitride bonds. So that means we have a copolymer forming, and that's actually also then improving later other properties, as I will show. So here you can see the processing steps. So first of all, you have the electrospinning. You have this the copolymer. You have the non-woven mat, which is still in the polymer state. Then you have the oxidation, so that means a cross-linking step, and then the pyrolysis at about 1000 degrees Celsius in nitrogen, leading to these non-wovens. And here you can see the microstructure, and as I learned from Richard Todd once, who was the editor-in-chief of the Journal of the European Ceramic Society, he was always saying to me, and remember, Stefan, microstructure, microstructure, microstructure. And so we look at the microstructure all the time now as in material science. So here you can see the thickness of the fibers and It's about 500 nanometers to 1 micrometer, so which is very small. And if you do not process them correctly, you also could induce health issues because nanofibers are actually hazardous. So that's why we investigated the affordability first of all. And to see, can you, oh no, how can I actually click on the video? Ah, yeah, there you go. Okay, that's the video. And I think it's the same PhD students. It's not a competition between two PhD students who has the better affordability. So we have on the right side, we have the printing paper, and on the left side, we have the non-woven after pyrolysis. And it was probably not performed in our lab because we have other gloves. So it was the chemistry lab. So for example, this is the printing paper and this is the non-woven, and there was not much difference even. And for example, the image F, for example, here is also showing after the fibers after folding, so there was no breakage actually of the fibers observed. And then what is also important, looking at the microstructure, or let's say of the structure of the fibers. So here, if you use Raman spectroscopy, you have the typical so-called G line, and also the D line for the amorphous carbon. And you see here you have the pure carbon fiber, and here you have the hybrid fibers, and you still see this D line and the G line. So that means actually the amorphous carbon was still present. Even if you use wax, you also have the same. You come to the same conclusion. So that means you have amorphous carbon inside. And what is then interesting, due to the amorphous carbon, you also have actually a good electrical conductivity, which is quite stable even over a large temperature range. And this also means the electrical resistance is quite low. And if you click, please, on the next video, you see actually, again, the foldability. It does not change even after a lot of cycles. So this is collaborated at the chair of polymer engineering, these experiments. And they have this kind of nice automatic machine. And we have to wait 5,000 times. So no PhD student was involved, at least a PhD student, but at least it was not his job to do it 5,000 times. And actually you see that actually the electrical resistivity was not changing a lot, even after 5,000 cycles of bending. And it's very interesting that it's foldable as the fibers, and the electrical conductivity is not changing actually a lot. The other aspect is actually that these fibers, they have a low thermal conductivity, which was very interesting. So we wanted to investigate not only the electrical conductivity, but also the thermal conductivity. But then we observed that their thermal conductivity actually is extremely low. So that's actually comparable to aerogels, which we found out. So that means it's has a very low thermal conductivity, and higher content of the siloxanes, of the organosiloxanes, actually leads to a lower thermal conductivity, which is also interesting. So that means actually the amount of the siloxanes actually plays a big role. And if you use an Ashby diagram and a database, you find out actually that the materials have, it's very unique because you have a low electrical resistivity, but the thermal conductivity is also quite low, which is actually quite unique. And usually it's coupled, the electrical and the thermal conductivity, but in this case it's actually decoupled in this kind of material. And the reason actually is, again, the microstructure. So we used STEM, and we found out actually that we have a so-called, we have a continuous amorphous carbon phase, and we then have a dispersed silicon carbon oxide nitride islands. They call it islands in the papers, or we called it islands, but I'm not so convinced. I would call it nano-composites. And that's the reason actually we have a lot of phonon scattering. That's the theory at the moment. And that's why we have this low thermal conductivity. And then actually we wanted to actually improve the oxidation resistance. And if you can click on the video again, please. So on the left side, we have these carbon fibers. And on the right side, we have the hybrid fibers. And you see actually they're quite oxidation resistant, which is so the aim of having a higher oxidation resistance compared to carbon fibers was also achieved. So which makes them also interesting, obviously, for ceramic matrix composites because oxidation resistance is a big issue. So I would like to sum up my talk. First of all, we investigate a lot of thermoplastics as a matrix material for ceramic matrix composites. So you can use, for example, PEEK filaments for additive manufacturing. We did this for short carbon fibers in the last years. We also have to optimize the cross-linking in air of these CFRPs, so CFRP technology is very important for us. And then we investigate the electrospinning of these hybrid polymers, leading to these very interesting nonwovens with an very interesting microstructure, and they have this very interesting properties that they have a low thermal conductivity, but a high electrical conductivity, as well as a high oxidation resistance. So I would like to thank you for your attention. I would also like to thank the funding agencies, the German Research Foundation, and I also have an announcement. Everyone who's interested in a postdoc or has a very eager postdoc to work in Bayreuth, I have funding from the Alexander von Humboldt Stiftung. For 2 PhD students, not postdocs, not PhD students, postdocs, for 2 years each, and everyone who's interested can contact me, please, because Humboldt fellowships are usually quite prestigious, and usually you have to run through a committee, and the funding rate is, the success rate is not so high. In this case, I was pre-selected as a so-called scout, so I scout postdocs, and then actually I'm the committee. So that means if I want to have one postdoc from abroad, then I can just decide and give this kind of postdoc fellowship. So thank you again for your attention, and I'm happy to answer questions.
Thank you, Professor Schafföner, for your very interesting contribution. Please, are there any questions?
About the final ceramization step, you use liquid silicon infiltration. Have you considered other ways, like polymer infiltration and pyrolysis, or chemical vapor infiltration, for example?
CVI not. So say it this way. So CVI is the only way, method that we did not try yet. And PIP, at the moment, PIP is not, let's say, our focus, but let's say typical like slurry infiltration, for example. We are good at slurry technologies at our chair. And so that's why a combination of with our slurry infiltration is currently one of the focus. And because I can say that because the publication is already on my desk, so slurry infiltration, for example. Yep.
Actually, I have also another question. Regarding the design of experiment of the fused filament production in 3D printing machine, the choice of the parameters have been dedicated to this application or are typical for all the final items that you need to achieve?
No, because the problem is, let's say, Of course, you have to read the let's say, literature of the CFRP for the CFRP production, but then you have the other processing step like pyrolysis and also cross-linking and also the siliconization. So that means actually maybe it's not the best microstructure for CFRP, but maybe the better one for the production of the ceramic matrix composites. So that's why actually we had to optimize that actually quite a lot. And even printing, so FFF of carbon fiber reinforced PEEK just for, let's say, in the polymer state is not, let's say, trivial. So yes, it's only one PhD student, his name is Wolfgang Freudenberg, and the other one is Jalena Best. Actually, they are more or less only working in the polymer state to optimize their processing. Yep.
Thank you.
So on a scale between carbon fibers and silicon carbide fibers and for oxidation resistance, where do you think these fibers are on this kind of range?
At 900 degrees Celsius application temperature without oxidation.
Okay.
Which is, let's say, if you compare this, I mean, like there are a lot of nickel-based alloys working at 900 degrees Celsius. And so let's say so 900 degrees Celsius. There's I think actually a large application field if you make it cheap enough. So that's why actually and I think these kind of fibers, they are competitive when it comes to price. I think compared to silicon carbide fibers, obviously. Yep.
Any other questions? Okay. Otherwise, let's thank again our speaker.